So welcome to the last talk of this afternoon. And this will be online talk by Christian Maes. Maes, I don't know if you have lost him already.
I'm here.
Here? Yes. Welcome, Christian. So the floor is yours. You are the next speaker.
Okay. Thank you. Thank you very much, Satya. And thank you for the organization. Apologies that I can not quite join you there in Bangalore, but let me start by wishing my best wishes and congratulations to Deepak for all the accomplished work, of course, and for being one of the very great inspirers and leaders in statistical physics and physics in general. I have been drawing a little flower just this morning, but I hope there will be many hundreds of flowers still blossom and schools of thought content. Okay, so the subject of my talk is quite general. It's about thermal properties of nonequilibria. That sounds very general because thermal properties, that's quite a bit, and nonequilibrium, that's also quite a bit. So we will try to combine these in somehow specific questions, but I think it's important to start by remarking that it's not so clear even what we mean by even the general words that we have here, and it is not something that is often addressed. And so this talk can be also understood as a kind of an introduction to a subject which I think is really worthwhile for further investigation. So in particular, one of the things that I have seen if I looked at the titles of the talks is that I will be speaking about a nonequilibrium extension of the third law, and that in particular is joint work with Vazek Kodabandelu and Karl Netochny, and we will come to that shortly. But first, if we speak about thermal properties, we have in mind the somewhat older scientific domain of calorimetry, but extended to nonequilibrium. And so there are a number of elementary first questions that we have to address, like how do we define at all heat capacities out of equilibrium? And why would we care to do that? Does it inform us indeed about, for example, low temperature behavior of non-equilibrium systems, or about things related to phase transitions and things like that we are used to in equilibrium? And also, like for setting the general scene at low temperature, is there something like an extension of the Nernst postulate? Now, in all that, one has to face basically the problem that we are dealing with non-equilibrium, and we cannot expect that all of that will be decided somehow by a unique entropy function, but we can expect that other aspects, which I have called frenzy, will start to play a role. Okay, so to remind ourselves, let me start by telling you about the miracle of equilibrium. The miracle being that, well, basically, if the thermodynamic potentials govern a lot. Let me call it just the entropy. It's essentially a unique entropy which decides whether a particular piece of matter is either a diamond or is it more graphite, while the more elementary microscopic degrees are very similar. So the transition from the microscopic laws to the macroscopic behavior and how to characterize the phases of matter, how to characterize the response is basically governed by the entropy. It's all about that unique entropy. And just to remind you of the various keywords that we find in courses on statistical mechanics, it's kind of remarkable that from the beginning already with Clausius, where the definition of entropy was given as a differential which equals the reversible heat over temperature, that entropy was a heat or related to heat, but surprisingly, miraculously, in the hands of people like Boltzmann and Planck, was related to degeneracy, to fluctuations. which became a very powerful object, of course, to understand the relation or the extension of thermodynamics in the direction of fluctuations. But not only is the entropy related to heat and fluctuations, there is also an H theorem, an arrow of time associated to it. It also appears in the so-called fluctuation dissipation relations. It governs linear response. And if that is not enough, we also know the entropic forces, or more generally the statistical forces, where such thermodynamic functionals are really potentials for a force, a thermodynamic force, that in the Newtonian sense of the word, that really have things to move. Now, well, you can also associate formulas to that, but I will not repeat them, except that I think it's still a good idea to make some kind of a t-shirt out of these formulas. But the point that is really the subject of this talk is, well, what about non-equilibrium? Well, first of all, the point is that this thing that happens in equilibrium with this unique entropy, one should not expect to be repeated if you go away from equilibrium. Somehow, while heat and degeneracy fluctuations, they seem to merge for equilibrium systems. There is no reason to expect that if you go away from equilibrium. If you go up the mountain of non-equilibrium, you see various smaller streams, rivers that are separate. So we do not expect anymore that the whole story will be told in some kind of obsessive use of entropy and thermodynamic functionals, but rather things like dynamical activity and accessibilities will start to matter crucially. Now, somehow that may seem obvious, but in practice, it seems like a lot of non-equilibrium physics still today is obsessed with entropy and its production, even though already since a long time, people like Landauer in 1975, and I just made here a copy of an important paper there, have stressed, and it has been stressed repeatedly, that entropy, entropy derivatives, entropy production are just not enough for characterizing the steady state. And he makes, and there the copy is a bit not very well done, but he in the end of the paper, he illustrates that with some conversation he had with Charlie Bennett about how to determine whether under a given set of planetary conditions, life is the preferred state or only a metastable state. And the conclusion is we cannot, how do you do that? You cannot just compare the state of lifelessness, the lifeless state, and the non-biological state. You must also invoke somehow the transitions between these states. You have to understand fluctuations, you have to go beyond ensemble averages, but the dynamic starts to enter in a much more important way. This somehow in this paper is summarized in what has been called nowadays the blowtorch theorem. So just to make it a bit more specific, even though not very much, if we take, well, try to imagine a non-equilibrium system with a dynamics which connects states of the system in a kind of Escherian way. You remember the Prince of Escher, where you can have stairs all the way going up, but somehow by some strange, maybe optical effect here, it turns out that while you're very up, you can also go up even more and go back to the place where you started, which seemed to be very much down. So that's a lot what is happening in non-equilibrium systems, namely the connections between states has not a kind of, it's not a gradient structure. But if we look at, say, at low temperature or at very large driving, and we connect our non-equilibrium conditions in a kind of graphical way, which is then a D-graph of preferred successors. Well, when it is strongly connected, I'm not going to enter here in the details, then one can easily verify that the low temperature asymptotics of the stationary distribution is inversely proportional to the escape rate. So that is just to mention one specific example of this blowtorch theorem, where clearly a kinetic aspect, here the escape rate, enters crucially to determine the occupation statistics. And everybody can make one's own example of even a small non-equilibrium system, which is Escher type, and where you can verify almost by hand, because you can do it for few state systems. You can verify that entropy production, thermodynamic functionals, or what can you define, they are much less important than, in fact, the real physics, certainly at low temperature or at low driving, is determined by more kinetic aspects such as accessibility, escape rates, dynamical activity, and so on. Okay, now, does that make us not hopeless? You know, I mean, if you speak about non-equilibrium, it's a bit like speaking about non-elephant biology, and that seems to be too much. Where should one start to get a bit of structure? Because if this whole framework of thermodynamic functionals falls, and naturally it falls, then what kind of systematics can we still expect? The non-equilibrium phenomena are extremely wide and varied, and it will be hard to have a general theory, of course, for them. But nevertheless, we can try to do something for classes of systems, very simplified models of systems. And why not try to do indeed start with heat capacities, which is a calorimetric quantity, because it has a proven record. I mean, if I remind you of situations in the end of the 19th century where heat capacities were really important keys for making the transition from classical physics to quantum mechanics. Even Maxwell, already in 1860, but it has been repeated by many others, were emphasizing that, you know, we have a great theory, molecular kinetic theory, except that we don't understand heat capacities. That was the problem for the low temperature. Dulong-Petit law did not work there. And so why not try to understand whether some kind of a thermal aspect like heat capacity for open systems, which are out of equilibrium, could also be physically informative. And maybe that's what we want to do, just to try. Okay, so the setup, as I was saying, will be extremely simple, and I will restrict myself for this talk to what we call jump processes. And to have an idea of what I mean here, just look at this graph here. So these vertices here that you see, they correspond to a particular state, at least on some level of description. It can be, of course, modeling already in itself a many-body state. But on this abstract level, we have a graph, and then we have edges. And what the arrows here mean is not that so much that there is a unique direction, but there is a bias. So even though the edges, you can go in two ways, this arrow just means that there may be a bias with a certain amplitude epsilon, and here it may be going in this direction, and here it may be going in the other direction. And there can also be, of course, edges like this one that has a rate alpha, which is symmetric in both directions. In fact, that kind of graph for those who are active in active particle systems is a kind of jump process model on the lattice or in the graph of a kind of run and tumble system, an active particle system. Okay, so what do we have? We have states which are denoted by X and Y typically. We have jumps in a certain way from over the edges, and we will denote by KXY the transition rates. So we think here about basically a unique random walker on that graph, but again, that unique random walker, it can really be a walker which is hopping between various many-body conditions. Now, the main start, which makes the transition to physics, because somehow for now that is just a mathematical setup, but the main thing that relates it to physics is the condition of local detailed balance. That is not such, well, an easy concept, but combining words and formulas, it basically means the following in this context. So I will always work with transition rates between over the edges, which are strictly positive, so these KXY here. And there is also an inverse, which is the KYX. If we take the ratio and the logarithm, we will attach a physical meaning to that. And the physical meaning is that this is basically the entropy flux in an environment which is at inverse temperature beta, so that the Qxy would be the heat which is given to that bath, to that environment, living at temperature T, and it is the heat which is given during the transition from X going to Y. So that is the thing that is has to be motivated, has to be understood. I have no time to really explain where that comes from, but that is basically the bridge that you make between your physical modeling with Markov processes here and heat. So of course, the origin of that goes back to recoupling limit and the understanding of what is the meaning of such a jump process if you derive it from a much more microscopic model, possibly a Hamiltonian dynamics here, or even a quantum dynamics, where you're working on the level of the Fermi golden rule. Okay, so for people who are like the fluctuation theorem, basically that is the same thing and equivalent with the fluctuation theorem, at least for Markov processes. So this is just the same thing. At least for one reservoir here, which is thermal, which is one of the temperature in beta, but the non-equilibrium will show in the fact that this Qxy, which is anti-symmetric, of course, in the exchange of X and Y, has a part which may be irreversible in the sense that it does not need to be a difference of energies. So in equilibrium, you will have, and then you recognize the global local detail balance relation. Qxy would be the difference of energies associated to the particular molecule or whatever driven or lattice gas you're studying. But in non-equilibrium, there is an additional part which need not be for all edges be given by the same difference of potential. Okay, so I repeat, the non-equilibrium enters in the fact that the Qxy is not just a difference of energies like it would be in detail balance, but local detail balance still allows us to associate to this Qxy the word heat associated to the transition from X to Y. Okay, so what should we now do for the next thing? Well, you know, maybe I will add a bit of formulas, but before I do that, let's see what we have in mind. So I tried to make here some drawing, but I wasn't very successful, I'm sure. But think about some battery which is driving a current through a resistor, maybe a very small resistor. So there is a current here which is maintained by some, well, the battery is doing work. And imagine all of that is sitting in an environment, maybe some water or other kind of substance at a certain temperature, maybe a certain density or chemical potential. Now, all the time, if we have such a non-equilibrium system in this environment, it is Joule heating. So there is always associated to that a particular flux to that environment. And it may depend on lots of parameters, and the parameters will be denoted by lambda. And this P lambda here that you see is this power which is dissipated. And we assume that before time zero, so here is time zero, that before time zero, we are happily living in this non-equilibrium steady condition, and that there is a dissipated power which we denote by P of lambda. So the vertical axis will be this dissipated power. Then let us imagine that at time zero, we are making a small change in the parameters. So here we were having parameters lambda, and now I change them to lambda plus d lambda, where d lambda is a small change. It could be a change in temperature. It could also be a change in intrinsic properties of the battery or in the resistor. I don't know. It depends, of course, on the non-equilibrium system, what kind of parameters we have. Well, if we wait long enough and we go asymptotically in time, then we will have a new steady state, a new non-equilibrium steady state, and there will be a new dissipated power associated to that condition. So in a way, what we are doing here is the very old habit that we have learned from equilibrium to understand the relaxation between stationary conditions. And here we are looking at a transformation between a non-equilibrium steady condition and another non-equilibrium steady condition. Now, it's not quite clear in my figure, but this transformation I am doing in a quasi-static way, but I will not formalize what I mean by that, but I just have it a little bit in the fact that I'm considering a very small change in this parameter. Anyway, after that change, you have a relaxation period, and this relaxation, okay, can be all kinds of things. But because we have this heating here and this heating there, there may be also an extra heating. And this is the excess heat, which is the thing that I am now coloring, and this is denoted by this dq of excess. This is the excess heat, which is entirely due to the fact that we are relaxing from one non-equilibrium condition to another equilibrium condition. So that is what we call the excess heat. So in contrast with equilibrium, where you do not have this dissipated powers stationary in the beginning or at the end, here we have them all the time. There is all the time this Joule heating, and we are looking at this excess heat. There are other definitions of excess heat, but the one that I'm taking here is operationally very useful, measurable, we would believe. And in fact, if one enters the mathematics, there is also a geometric expression for that excess heat, which is very similar somehow and very analogous to what you have in equilibrium. Okay, so excess heat is in this way defined. And in formulas, you do like that. So remember that the local detail balance was giving us an heat during the transition XY. This happens at a certain rate. This is the transition rate, you remember. And so if we are looking at the expected heat flux or the expected power when you're in non-equilibrium condition X, then you just sum over Y, and this P lambda X is what we're calling the dissipated power at X. Now, if we want to come to terms with this excess heat that I defined also in my previous thing, then the quantity which perhaps intuitively already could be clear is the following. We call it the quasi-potential, and it is denoted by V lambda. It's a function of X, and it's a time integral. It's a time integral of an excess in powers. So let us first look here. This is the stationary power when we are having the parameter values lambda. So this is just the stationary power. And then here, this first term, that is a transient thing because it happens at time t. And we are looking here at the expected power that you have at time t when all the time you have at time 0 started from X. So you should think of, indeed, I prepared my system here in my stationary condition. Of course, this has some fluctuation, and perhaps I am sampling here a certain X from this initial distribution, and with that X, I then relax towards the new stationary thing, which would be corresponding here not to the lambda, but to lambda plus d lambda. Anyway, I think it's kind of intuitively clear, and I'm not doing the quasi-static analysis here, that this quasi-potential is could be exactly related to that excess heat as the time integral of the excess power. So it's like an infinity minus an infinity, which is exactly taking care of this, this excess heat here. Okay, so that's we call the quasi-potential. And then if there is a theorem, if you wish, the excess heat towards the system, at least for elementary changes in lambda, is exactly related to that quasi-potential. I'm not discussing that, but I take it for granted in this talk that somehow the excess heat is completely, in the quasi-static approximation, is completely determined by this, excess heat is completely determined by this quasi-potential. All right. So just to repeat the main things, I stress that we assume the condition of local detail balance, and for simplicity, I just imagine one heat bath at inverse temperature T, to which the heat is dissipated, and that heat is given in the QXY. Then we have the expected heat flux in a certain non-equilibrium condition X, which is measured by that heat and the transition rate. And then the excess heat is completely determined by the so-called quasi-potential, which is the time integral of an excess between the power at time t and the stationary power, possibly here I put the lambda prime in the new parameter lambda, while the x will be drawn from the old or original non-equilibrium condition. So that is the kind of the mathematical setup. And I repeat, you just start to do that on a general, your preferred finite connected graph, which you obtain perhaps from your favorite model, which at least is a physical meaning because of the condition of local detail balance. All right. Now, the upshot of everything here is here in the box. So just look at this condition. So the excess heat that we are interested in is then, if you make the, I mean, there is also a row around, which is the stationary distribution that I have not spoken about so far. So finite system, Markov jump process, there is a unique stationary distribution. And this excess heat is in fact given by the covariance between our quasi-potential, which is defined here, and the differential of the logarithm of this stationary distribution. By the way, just to see what happens in equilibrium, well, in equilibrium, this quasi-potential is basically the energy minus its average energy. But okay, and this is a covariance, so the average will not matter. So in equilibrium, this will be the energy. And the derivative of log rho, well, rho would be the canonical equilibrium. So in other words, that would be again related to the equilibrium. Take derivative with respect to beta, for example, that will give you an energy again. So in other words, in equilibrium, you find the usual expression that the heat capacity for the canonical ensemble is given by the variance of the energy. Here in non-equilibrium, we have the heat or the quasi-potential, which is encoding that heat, which is in covariance with, okay, the change in log rho. And this log rho, well, that is in fact the expression that more is associated to Boltzmann, of course. This is related to the occupation level distribution. So here you see that in non-equilibrium, if you take the excess heat, it's no longer related to a variance, but it is related to a covariance between the Clausius aspect of the entropy and the Boltzmann aspect of the entropy. And now I have been making so much drawing that you can no longer read it. But that is the first instance of non-equilibrium that you see, that you go away from all the time being the energy or the entropy, but it is related now to the heat, which is correlated or anti-correlated, it's a covariance with the Boltzmann entropy. All right, now let us start to give a bit of specific examples here, but maybe the chairman can tell me how much time I have left.
10 minutes.
10 minutes, okay. So here is a specific example to make it more concrete, and it's on the graph, it's just 4 states. So that's the simplest one you can imagine. And you can imagine it in the following sense. So it's a 2-level system. You see here the 2 levels. This one you can call 0 level or the 0 state, and this is the 1 state here. So here is the 1 state, here is the 0 state. But the potential is flipping at a rate alpha. So in other words, you get this kind of pedaling motion of the potential, in which either the 0 state or the 1 state becomes the global minimum. All the time, we have transitions between the 0 and the 1 state, but it depends now whether you're in the plus potential or in the minus potential, and you can see that indicated in this notation, whether it is easy or not to bridge the energy epsilon. So for example, if you're in the minus state, which is what I'm saying here, suppose you're in the minus state, then it's not so easy to go from the 0 to the 1. But when you're in the plus state, it's more easy to go from the 0 to the 1 because the epsilon I'm taking here positive. Okay, so it's a usual 2-level system. It's a usual kind of most simple model you can imagine, just a 2-level system, except that what you call the upper and the lower one is changing. It flips at a random, well, it flips at a rate alpha. So in other words, if I look in time, and that is this picture here, if I look in time, and I have these 2 states, for example, here is the 0 state, here is the 1 state. So I start in the 0 state. then it can be that the potential is flipping, in the sense that I go from one, either the 0 or the 1 is minimum, and then I remain in the 0 state. But then at a certain moment, being in some potential, I go to the 1 state. That is this transition here. Then, of course, there is heat, which is released. And then again, I can change colors. The colors here mean in what type of potential you are, but the heat which is released is only at that moment you're jumping between the 0 and the 1 state. And depending whether you're in the, bluish green color or in the reddish orange color, only then that decides whether the heat is released is either epsilon or minus epsilon. That is the simplest model you can imagine of a non-equilibrium extension of a two-level system, for which we can immediately calculate everything, and including here the heat capacity. And this heat capacity is, maybe I did not say it very much, but it is basically the excess heat per temperature. And you see these typical things that you find for the equilibrium two-level system. In fact, the equilibrium two-level system is the blue curve. And what you're seeing is that there is a magnificent increase, in fact, of the heat capacity. You see these peaks here, these narrow peaks, which happen if you have the switching. So for example, in alpha equal 4, you have this largest peak here at even lower temperature. By the way, you just also see that even in non-equilibrium, the heat capacity goes to 0. Now, you can make it even more, you can also take into account not only that you have an energy level, but also that you have this kinetic barrier, and you can include an Arrhenius factor, which also scales with beta. And then you can also have negative heat capacities, which are unseen, of course, in equilibrium. So now you have a two-level system. And because of the switching, you have low temperature, the signature of a negative heat capacity. And in other words, if you would measure that, you can understand that there must be a kinetic barrier at low from seeing the negative heat capacity. So in other words, already here, even though the system is very simple, you can already understand that there is information really in this heat capacity, and much more than in equilibrium. For example, you also see kinetic aspects. You see not only this switching between the potential, but also you see the kinetic barrier, which is in the individual system. So these non-equilibrium heat capacities can reveal that. Now, there are many other systems you can try to do. I'm not going to discuss this here, but these are simulations and also calculations, actually, which are done by Prita Dolai for active systems. So, for example, the famous run and tumble particles, you can now compute and simulate, depending on the parameters in the system. You can do the same thing as before for the quantum switch, and you can try to understand how it depends, this heat capacity, on tumbling rates, which are the alpha, or on propulsion speeds. For example, for high propulsion speeds, how you will see negativity of the heat capacity. Or you can take an interacting system like in a lattice gas, but which is driven. So here, for example, is a cartoon where you have in white here, you have a surrounding temperature or chemical bath with a certain chemical potential. This chemical potential is feeding these kind of quantum dots. And then when there is a particle, there is a driving zeta, which takes you around the circle. So this is like a coupled system of something like in semi-classical quantum dots. Characterized by temperature, chemical potential, and the driving, which takes these particles in a circle, like in the usual ASEP, except that there is here the birth and death process. So here also you can calculate the heat capacity. This is, for example, in a three-state system, but in fact you can do it for any size of the system, and you can get explicit formulas for the heat capacity and try to understand what is the sign of the various parameters, like the chemical potential, the temperature, or kinetic barrier, which is the A, in the presence of heat capacity. And what you will find is, in fact, that at 0 temperature, you get a phase transition, in the sense that if I look to the chemical potential, that there will be regions, and they depend on the kinetic barrier, where the heat capacity jumps from being 0 at 0 temperature to infinity at 0 temperature. So you get an enormous 0 temperature transition. A yes or no question is satisfied here, depending on the chemical potential, whether the heat capacity is going to 0 at 0 temperature or not. And that, of course, invites to understand what is really behind that Nernst postulate for non-equilibrium jump processes. And what we have been showing in collaboration with Fase and Karel is that you get that the heat capacity and also the excess heat more generally is indeed vanishing, going to zero with zero temperature under conditions which are an extension of what you have in equilibrium. So, you know, in equilibrium, the third law is not something which follows just from the general framework of statistical mechanics. You need conditions for that. And basically it amounts to the fact that you should not have residual entropy, or there should be not a lot of disorder at zero temperature. So you can say it's like a non-degeneracy condition. It suffices for having a third law of thermodynamics. When you go to non-equilibrium, there is a second condition which needs to be satisfied. And we have called it a non-uniform delay, which is related to the fact that one needs to avoid a localization condition. And I think I will try to finish this talk by trying to explain a little bit where that comes from. Okay, so remember that, well, maybe we don't want to remember, but we want to look here. Here is the, you know, I would like to remind you of this formula here, which is the excess heat and which is also related to the heat capacity. So this excess heat is basically a product of the heat of the quasi-potential, which is related to excess heat, and the change in stationary distribution. So if you want to have that go to zero, the strategy is simply by saying, well, this one, we would like to go to zero, and that one, the quasi-potential, we'd like to have it bounded as you go to zero temperature. So now the fact that the change in the stationary distribution goes to zero at zero temperature, that you can make sure by the appropriate conditions on non-degeneracy at zero temperature. Somehow you make the typical analogy with ground states in equilibrium to say that the stationary distribution should be at zero temperature. The stationary condition should be like a condition which is well isolated from the rest of the system. So that is not a problem. The real mathematical challenge is to prove that this quasi-potential remains bounded, uniformly bounded as the temperature goes to zero. So basically there are two strategies. This quasi-potential, if you look at the difference between an edge, so x and y, or just in my graph, they are just two non-equilibrium conditions which are coupled in transitions. If you take the difference, it's no longer an excess, but you have to look at the differences in the dissipated power. Now, in probability theory, there is a way to understand this because you're really working with a random walk on a decorated lattice with initial conditions which are just different, and you can use coupling methods to prove boundedness. And that leads to physical conditions for the third law, which are related to, well, that the relaxation times have to be small with respect to the dissipation times. You see, the x and the y, they have to meet somehow. At some moment they have to meet, and you have to understand that as this meeting time, as its function of temperature, should be sufficiently small with respect to the dissipation time, and the dissipation time is basically, but not quite, the currents that you have in the system, or the inverse of the currents. Of course, if you're in equilibrium, the current is zero, so this dissipation time goes to infinity, and that's always true. But in non-equilibrium with the currents, you have a non-zero dissipation time, and you still have that these meeting times must be sufficiently small. Now, this condition, while it is kind of physically interesting, realistic sometimes, and pleasant, there is a second method, and here is the second method. It is related to just solving for the quasi-potential, basically. Now, this quasi-potential is defined as an integral, but it's easy to see that the quasi-potential solves linear equations which are written here. So it's a solution of a large set of linear equations. And here, Fase Corabandelu, our collaborator in this project, discovered that, in fact, using the matrix Forest theorem, you can get explicit control over this quasi-potential. Maybe you remember the Kirchhoff formula, which is really an instance of the matrix 3 theorem on graphs to express in very general ways the stationary distribution. Well, for such non-equilibrium systems, there is also a general method to solve them, which is called the matrix Forest theorem, which gives an explicit expression for this quasi-potential. And I just have it here in this last line here. It's related to weights, which I'm not going to explain, but instead of trees, it's basically you have forests which consists of 2 trees, basically. And the advantage of these explicit formulas is not that they are there in general, they are too general to be useful, but the point is that if you go to the 0 ambient temperature, if you really go to vanishing temperature, then such formulas become useful. You know, it's like Kirchhoff formula is in general not very useful, but if you go to the extremes of very low temperature or very large driving, these things become useful. And here is the same thing, that if you take this matrix Forest theorem expression for the quasi-potential, it becomes useful and it becomes possible to show the right conditions under which this quasi-potential remains bounded. And together with the non-degeneracy of the stationary distribution, it gives rise to this extension of the Nernst postulate. Okay, I think I'm stopping here, but that was basically the main thing I wanted to say. Thank you
very much. Questions? Yeah,
Hi, Chris. So, I mean, so how difficult is this? I mean, to measure this excess heat experiment in an experiment with, let's say, just electrical current, and we change the voltage.
Yeah, well, you see, I have not been discussing this in my talk, how you measure that, because I have somehow given the mathematical framework with the quasi-potential. It turns out that there is a method which is called AC calorimetry, where you are not doing what I told in the talk, but where you take a modulation of the temperature, which allows you to understand that the out-of-phase component of the heat flux that you will see, that this is related to the heat capacity. So somehow what we have is we have a theory which makes it interesting. We have even a method to measure it, also useful for numerical tools, but it remains true that we have no experiments. At least I do not know of experiments who have been taking up that challenge of going to low temperature non-equilibrium heat capacities. Perhaps because it has not been really been studied and the framework has not been given before, but at least we believe that using this method of AC calorimetry, one gets indeed information about the thermal properties of non-equilibrium systems, but it still needs to be done.
Other questions? Christian, I have a question, in sort of a simple question is, if you go back to the slide where you showed this run and tumble particle, the heat capacity for the run and tumble particle.
This one.
So actually, I mean, if you can remind me how you actually, given the telegraphic equations for a single particle, how actually you measure this C of t here, and this for the curve on the left-hand side?
Okay. So we do not, of course, use the Fokker-Planck equation, but we start with the Langevin equation. Actually, you see it here to the right. This is the equation 4, the Langevin equation. So in Langevin equation, you see the position of the particle, which is changing in time. Here you have the propulsion speed, and the sigma t is plus or minus 1. The flipping between that is the tumbling part and also the running part. And then we have possibly a confining, or depends, a periodic potential U. And then we have our thermal environment, which is the usual white noise. Now, from such an equation, you can go to, via a condition which is similar to local detail balance, you can go to the the notion of heat. So the notion of heat basically has to do here with the fact of why is there an eta t? There should be not an eta t here. So the notion of heat is just because the position is changing, it will mean that the energy is changing. So the V here, that is in this framework interpreted as the work which is done on the particle, and the changes of energy is then related to the heat that you have. So if your position is changing, you get another energy, so you get the heat. So if you have a heat, you can go to the heat flux, you can go to the stationary heat. What you're then going to do is to change the temperature and to understand how the excess heat, so if you change the temperature, there will be an excess heat, meaning a change in that heat flux, and that per unit of temperature is what we are plotting here in the heat flux. Okay, so if there is no tumbling, if the V is equal to 0, this is the usual equilibrium heat capacity, which is this gray curve here. That is for propulsion speed equal to 0. That's the usual heat capacity which you would associate to such an equilibrium system with a potential U. And if you start to tumble and you start to have a non-zero propulsion speed, that's how you see the other curves. And they, of course, modify the equilibrium because the kinetics is different, because the dynamics is different. And for example, here also, you see how you get this low temperature peak. Of course, if you really think of run and tumble particles as associated to biophysics, you probably are not interested in low temperature, but if you're interested in, like in general molecular motors or morphing materials, new materials, then perhaps you are interested in low temperature, and it may be useful to understand how the non-equilibrium features change the heat capacity at low temperature.
Okay, thank you. Are there any other question, comments? If not, let's thank Christian again.